Good morning, students. This is Arvind, Assistant Professor, Department of EEE, DBS IT Kavali. So, in the previous class, I discussed about phasor diagram of a single phase transformer, both on-load and off-load conditions, that is no-load conditions, and EMF equation of a single phase transformer, and some problems on EMF equation and voltage transformation ratio. And now in this class, I am going to discuss equivalent circuit of a single phase transformer and the effect of non-linear BH curve on magnetic core material. Okay, firstly I will start with the equivalent circuit of a single phase transformer. Okay, so an equivalent circuit is merely a circuit interpretation of the equation which describes the behavior of the system. So an equivalent circuit is a circuit interpretation of the equations which describe the behavior of the system. So that's why I am taking this diagram. So this will explain how the circuit is actually equivalent circuit for a single phase transformer. So in this one I am taking a transformer with magnetic core and windings, okay, both primary and secondary. So on the left side we have the primary winding connection, and on the right side we have the secondary winding connection. So come to the left side of the diagram, we have the primary winding. So this primary winding is connected to the supply voltage through resistor and reactor combinations, and also with the parallel combination of R0 and X0, that is no load. So R1 X1 means it is at load, and I1 that is also at load. And here I am taking no load conditions, that is R0 X0. So it consists of the two components, that is IW and IMU, that is magnetizing component and working component. Like that we have different components. I have discussed this one in the previous classes in the phasor diagram. Okay, so on the right side we have the secondary winding connection. So the secondary winding is connected to the load, that is ZL, and it also connected to the resistor and inductor combination, and it also consists of the EMF E2 and the current I2 and voltage V2. So an equivalent circuit is merely a circuit interpretation of the equations which describe the behavior of the system. Okay, so the figure shows the equivalent circuit of a transformer. I have explained this one. And next, coming to the equivalent circuit of a transformer. So firstly I will take under no load condition. So under no load condition, what will happen? The primary of a second transformer draws no load current I0. Okay, draws no load current I0. So that is this one. Okay, so this one I0. So at no load the primary draws a current I0. Okay, next, it mainly used to supply the iron loss. Okay, it is mainly used to supply the iron loss. That is I0. The no load current by I0 is mainly used to supply the iron loss and to produce the flux in the core. Okay, so under no load condition, the primary of a transformer draws no load current, that is I0. It is mainly used to supply the iron loss and to produce the flux in the core. So the effect of iron loss is represented by a non-inductive resistance R0. Okay, the effect of iron loss is represented by a non-inductive resistance, that is R0, and the magnetizing current is represented by IW or IMU, is represented by X0. So in this diagram, you have that one. Okay, so X0. So this will give the magnetizing component, that is IMU. Okay, and next, so both of them are connected in parallel with primary winding. Okay, the effect of iron loss is represented by a non-inductive resistance, that is R0. So that is a parallel connection. Actually we have the primary winding, so it is connected to the supply voltage V. Okay, and it is also connected across the resistor R1 and inductor X1, and it consists of current I1. And we are taking under no load condition means the primary of the transformer does no load current I0, and it is mainly supplies the iron loss and it produces the flux in the core. But the effect of iron loss is represented by a non-inductive resistance R0. That is the additional diagram we drawn, across the primary winding, that is R naught and X naught. In that one, R naught connection gives the effect of iron loss, is represented by a non-inductive resistance R naught, and the X naught, that is the parallel to the R naught, it is gives the magnetizing current, that is I mu. Okay, so both of them are connected in parallel with the primary winding. So if you observe the diagram, the connection, that the R naught and X naught connection is connected parallel to the primary winding. So this circuit is known as exciting branch or no load branch. Okay, this circuit is known as exciting branch or no load branch, that is R naught and X naught. Okay. Next, that is shown in the diagram, that is this one. Okay, this diagram. And next, we are moving to another one, that is in that equivalent circuit. Okay, that is the first diagram. From that circuit I am taking the parameters. That is, in the diagram we have R1 and X1 terms. R1 and X1 parameters we have. So there R1 means primary winding resistance and X1 means primary winding reactance. Both are in ohms. Okay, and next R0. So R0 is the no load resistance in ohms, and X0 we have, that is no load reactance in ohms. So no load resistance and no load reactance, that is R0 and X0. And next we have I1, that is the full load primary current. Okay, I1 is the full load primary current in amperes, and I0 is the no load primary current in amperes. No load primary current in amperes. And next we have I2 dash. And next we have I2 dash, that is the load component of primary current in amperes. Okay, I2 dash we have, that is the load component of primary current in amperes. And we have IW and IMU. So IW is the working component and IMU is the magnetizing component. Okay. And next we have E1, that is the induced EMF in the primary winding in volts, and E2, that is the induced EMF in secondary winding in volts. Okay, next R2 X2, that is the secondary winding resistance and reactance in ohms, and ZL, that is the load impedance in ohms. So, and I2 we have the full load secondary current in amperes, and K we have, that is the transformation ratio. So these are the various parameters we have from the equivalent circuit. Okay, and next coming to the equivalent circuit of a transformer, that to refer to primary. Okay, so equivalent circuit of a transformer refer to primary. So the diagram is like this. So this is the equivalent circuit of a transformer referred to primary. So in this one, if all the secondary parameters are transferred to primary side, okay, if all the secondary parameters, that is R2, X2, V2, ZL, like that, all are transferred to primary, okay, we get the equivalent circuit of transformer referred to primary, that is like this. So in this one, actually we have R0, X0, R1, X1, I1, V1, E1 and I2 dash we have, normally we have from the previous circuit, and additional to this we are transferring R2, X2, that is after transferring we have the terms like that R2 dash, X2 dash and V2 dash and ZL dash we have. Okay, after transferring we have these terms. Okay, next note that when secondary parameters are referred to primary. Okay, note that when secondary parameters are referred to primary, resistances and reactances are divided by K2. Okay, please note this point. So note that when secondary parameters are referred to primary, in that one the resistances and reactances are divided by K2 and voltages are divided by divided by K square, not K2, this K square, and voltages are divided by K and currents are multiplied by K. Okay, these are the 3 points we have to concentrate. So when secondary parameters are referred to primary, resistances and reactances are divided by K square, voltages are divided by K and currents are multiplied by K. Okay, and this circuit is also called the exact equivalent circuit of a transformer. Okay, this circuit is also called the exact equivalent circuit of a transformer. So from the above 3 points, we are writing R2 dash is equal to R2 by K square and X2 dash is equal to X2 by K square. That is the reactances and resistances. So already I mentioned that secondary parameters are referred to primary. At that time, the resistances and reactances are divided by K2. So R2 dash is equal to R2 by K square and X2 dash is equal to X2 by K square. This R2 and X2 is the secondary resistance and reactances. And I2 dash is equal to K into I2. So I2 dash is the load component on the primary line. So that is I2 dash is equal to K into I2. Why we are taking K into I2 means the currents are multiplied by K when the secondary parameters are referred to primary. That's why I am taking I2 dash is equal to K into I2. Here I2 is the secondary current. And we have ZL dash, that is the impedance. So impedance ZL dash is equal to ZL by K square. So here ZL is the load impedance of the secondary side. So ZL by K square, that is ZL dash, and V2 dash. So V2 dash is equal to V2 by K. That is the voltages are divided by K when the parameters are referred to primary. So V2 dash is equal to V2 by K. Here V2 is secondary voltage. And next R0. So R0 is the no load. That is the effective loss component, that is R0 is equal to V1 by IW. So R0 is equal to V1 by IW. You know already from the Ohm's law, R is equal to V by I. So in this one I am taking R0, that is equal to V1 by IW. This IW is the working component and X0 is equal to V2 by I mu. So here I mu is the magnetizing component. So V2, that is the secondary voltage. So R0 is equal to V1 by IW and X0 is equal to V2 by I mu. So coming to the approximate equivalent circuit means the no load current, that is I0. The no load current I0 is only 1 to 3% of rated primary current. Okay, the no load current I0 is only 1 to 3% of rated primary current. So I2 dash practically equal to I1. So I2 dash is practically equal to I1. Okay, so due to this, the equivalent circuit can be simplified by transferring the exciting branch to the left portion of the circuit as shown in the figure. So for the equivalent circuit, we are simplifying the circuit by transferring the exciting branch, that is R0 and X0, to the left portion of the circuit. It is shown like this. Okay. So actually in the previous diagram, there is the exact equivalent circuit. We have this R0 X0 combination towards load, but in this diagram I am transferring this R0 and X0 towards supply voltage, that is V1. We have the combination like this. Okay, so this is the diagram. So actually it is in between R1 X1 R2 dash X2 dash, but in the approximate equivalent circuit, this combination is moved towards the voltage, that is in the R1 X1 region. Okay, and this circuit is known as approximate equivalent circuit of the transformer. Okay, next here this is the diagram. So the figure shows combined R1 and R2 dash, X1 and X2 dash. So previously in the diagram we are having separate R1, R2 dash, X1 and X2 dash, but here I am combining R1, R2 dash and X1, X2 dash. So R1, R2 dash is combining with R01 and X1 and X2 dash is combined with X01. So that is R01 is equal to R1 plus R2 dash and X01 is equal to X1 plus X2 dash. So from these things we are writing Z01 is equal to root of R01 square plus X01 square. So that is impedance is the combination of resistance and reactance. So here Z01 is equal to root of R0 1 square plus X0 1 square. Okay, here we have V2 dash, Z0 dash, Z01, I2 dash, I1, I0, R0, X0 and V1. Like that we have. And the above figure shows all parameters referred to primary, that is this one, this diagram. And next, similarly, the figure shows below is all parameters referred to secondary. All parameters referred to secondary. So previously, we have the diagram. So in that one, we are referring the secondary parameters all to the primary, and in this one, I am referring all the parameters referred to the secondary. So the diagram is like this. So here we have R02, X02. Both are combination. We have Z02 and we have V2, R0 dash, X0 dash, IW dash, IMU dash, and I0 dash and I1 dash. So here all the parameters in the primary winding is referred to the secondary side. So it shows all the parameters referred to secondary like this. Okay. And next, from this one I am writing R02. So actually here I am representing with R02. So that is R02 is equal to R1 dash plus R2. So that is equal to R1 k square plus R2. And X02 is equal to X1 dash plus X2. So that is equal to X1 k square plus X2. So from that one I am writing Z02 is equal to root of R02 square plus X02 square. Okay. Next, that is the explanation for the equivalent circuit of a single phase transformer. And next, coming to the magnetizing current concept. Okay, already I discussed this magnetizing current concept in the transformer on no load condition in the previous classes. And now I am going to discuss same here, that is the magnetizing current. So magnetizing current means when the AC power source is connected to a transformer. Okay, when the AC power source is connected to a transformer, a current flows in the primary winding, even when the secondary winding is open circuited. Okay, when the AC power source is connected to a transformer, a current flows in the primary winding, even when the secondary winding is open circuited. So this is the current required to produce the flux in the ferromagnetic core. Okay, this is the current required to produce the flux in the ferromagnetic core. So it consists of these components. Those are first one is the magnetization component, that is IM, and second one is the core loss component, current IE. So firstly we have the magnetization current IM, that is the current required to produce the flux in the core of the transformer. So the current required to produce the flux in the core of the transformer. And we have the core loss current IE, that is the current required to make up for the hysteresis and eddy current losses. So the current required to make up for the hysteresis and eddy current losses. Okay. So next, so for any coil, you know that already, for any coil E is equal to N into d phi by dt always. Okay, E is equal to N into d phi by dt. So if E is the applied voltage and phi will be the flux produced. So from this equation, E is the applied voltage and phi is the flux produced. And if phi is the applied flux to the coil, okay, and E will be the EMF produced. Okay, so let's look at this step by step. So I will explain this one by the step by step. That is first one. When there is no load on the secondary side, that means the secondary side is open condition. E is the EMF applied to the primary coil. So E is EMF applied to the primary coil. Then the coil will produce flux phi in the core. Okay, then the coil will produce flux phi in the core. And you can see that if E is sinusoidal, flux will be sinusoidal, cosinusoidal. That means I already explained this one in the EMF equation of a transformer. So you can see that if E is the sinusoidal, flux phi will be the cosinusoidal. So the coil will consume that much current as required to produce the flux. Okay. the coil will consume that much current as required to produce the flux phi. And next, so since flux phi is equal to N into I, that is number of turns into I, that is reluctance of the core, we can calculate what will be the current required to produce the flux phi. Okay, since phi is equal to N into phi, Ni, that is Ni by reluctance of the core, we can calculate what will be the current required to produce the flux phi. Okay, and this current is the magnetizing current. Okay, so since phi is equal to N into I by reluctance of the core, we can calculate what will be the current required to produce the flux phi. This current is known as magnetizing current. But since there is co-sinusoidal flux in the core, you know already this one, the same rule applies to the secondary coil, and there will be EMF induced in the secondary coil is given by E2 is equal to N2 into d phi by dt. So when you connect load to the secondary, up to now we discussed the load is not connected to the secondary, and now you connect load to the secondary, then there will be secondary current. So that is the secondary current flowing in the secondary coil will produce flux phi 2, which will be in opposition with the flux previously being produced by the primary coil. Okay, the secondary current flowing in the secondary coil will produce secondary flux phi 2, which will be in opposition with the flux previously being produced by the primary coil. That is the primary magnetizing current. Okay, so in effect, the net flux in the core will reduce it to phi minus phi 2. That is phi to phi 2. And but since EMF is still being applied to primary coil, okay, since EMF is still being applied to primary coil, it demands that the flux linkage of primary coil still be phi. Okay, since the EMF is still being applied to primary coil, it demands that the flux linkage of primary coil will be phi. So what happens is the current in the primary coil increases, so that it now produces the flux, that is phi plus phi 2, so that the net flux linkage of the coil becomes phi plus phi 2 minus phi 2, that is equal to phi again. Okay, so what happens is the current in primary coil increases, so that it now produces the flux, that is phi plus phi 2, so that the net flux linkage of the coil, that is the flux in the core, total flux in the core, that is become phi plus phi 2 minus phi 2, that is equal to phi again. So the additional current required in primary coil to restore the flux will not be equal to the current in the secondary unless number of turns are the same in both of the coils. Hence, the secondary current that flows when load is connected to the secondary coil will be reflected in the primary coil on the top of the already presented magnetic current. So not as replacement for it. Okay. So hence the secondary current that flows when load is connected to the secondary coil will be reflected in the primary coil on the top of the already presented magnetizing current. Okay, so that is the magnetizing component current, that is the explanation for this one. And we are moving to the next concept, that is effect of non-linear BH curve of magnetized for magnetic core material. So before going to this one, we have to know what is meant by BH curve. Okay, the curve plotted between flux density B and magnetizing force H of a magnetic material is called BH curve. Okay, the curve plotted between flux density B and magnetizing force H of a material is called B.Tech curve. So the shape of curve is non-linear. So you know already this one, the shape of curve is non-linear. So this indicates that relative permeability of a material is not constant, but it varies. Okay, this indicates that relative permeability, that is mu, of a material is not constant, but it varies, that is mu suffix T is equal to B by mu naught into H. So BH curves are very useful to analyze the magnetic circuit. Okay, BH curves are very useful to analyze the magnetic circuit. So if value of flux density and dimension of magnetic circuit is known, than from BH curve, total ampere turn can be easily known. Okay, if value of flux density that is B and dimension of magnetic circuit is known from BH curve, total ampere curve can be easily known. Total ampere turn can be easily known. That is, so this is the BH curve we are taking. So here the graph is drawn between flux density B and the magnetizing force H. So here we have the curve is like this. So up to B point we have increasing manner, so slightly increasing manner, and now this further increases to C point. So this because ferromagnetic material, if you use the ferromagnetic material, we have the BH curve like this. And next, the phenomenon of lagging behind of the induction flux density B behind the magnetic force, that is the magnetizing force H in magnetic material, is called magnetic hysteresis. So the phenomenon of lagging behind of induction flux density B behind the magnetic force H in magnetic material is called magnetic hysteresis. So hysteresis loop is a 4 magnetic BH graph from where hysteresis loss, corrosive force and retentivity of magnetic material are obtained. The hysteresis loop is a 4 quadrant, that is 4 quadrant, we are considering 4 quadrants BH graph from where hysteresis loop, coercive force and retentivity of magnetic material are obtained. So to understand this hysteresis loop, we are supposed to take a magnetic material, we are supposed to take a magnetic material to use as a core around which insulated wire is wound, around which the material. So I will show the diagram, after that you will understand. So here this is a circuit diagram to form magnetic hysteresis. So here we have a core, it is wounded with a wire and it consists of a variable resistor and a voltage source, that is V, and it consists of the magnetic flux, that is this one. Okay, so that means to understand hysteresis loop, we are supposed to take a magnetic material, so it uses as a core. So we are taking a magnetic material, so it uses as a core around which insulated wire is wound. So the coil is connected to the supply, that is this one, supply V, okay, that is DC, through variable resistor, that is this one, variable resistor, this one, okay, it consists of to vary the current I. Okay, the coil is connected to the supply through the variable resistor to vary the current I. So we know that current is directly proportional to the value of magnetizing force H. Okay, we know that the current is directly proportional to the value of magnetizing force, that is H. Okay, based on that, so when the supply current I is 0, so when the supply current is I is 0, so no existence of flux density B. So at that time, no existence of flux density B and magnetizing force H. So the corresponding point is 0 in the graph above. 0 in the graph above. So in this one. Okay. So this is the magnetic hysteresis loop we are considering. So here I am taking the 4 quadrants. Okay, so in this one I am taking B minus B and H minus H. So you know already B means magnetic flux density and H is the magnetizing force, capital H. So we are drawing a graph of the curve like this. So this is the magnetic hysteresis loop. So here the current is 0. At the time we are not having the B and H. Okay, so here we are BR, that is the residual magnetism, and HC is the coercivity. Okay, so here we are BR and HC, and we have minus H, so minus HM and plus HM. So we are considering the points, that is small a, B, C, D, E, F. Like that we are considering the curve is drawn from third quadrant to second quadrant through the first quadrant, and third quadrant through fourth quadrant and first quadrant, and second quadrant we are taking this one. So we are mentioning, we are representing with the dotted line from plus BM and minus HM for plus HM in the second quadrant, and next we are having minus BM, minus HM, and minus H. Like that we are having in the third and fourth quadrant and first quadrant also. Okay. So now B gets reverses following path. Okay, now B gets reverses following path C to D. So if you see this diagram, so the magnetic flux density B is flowing, gets reversed following path C to D. It reverses from path C to D. So this one. So it reverses. Okay. So at point D. So observe this one. So at point D, it is on the third quadrant. Okay. So at point D, again magnetic saturation takes place. Okay, again magnetic saturation takes place, but in opposite direction with respect to the previous case. Okay, but in opposite direction with respect to previous case. Okay, at point D, B and H get maximum values in reverse direction. Okay, at point D, B and H gets maximum values, but in the reverse direction. That is minus HM and minus BM. At point D, we have this thing, minus HM and minus BM. That is in opposite direction. So, if decrease the value of H in this direction, again B decreases following the path D. Okay, that is minus B and minus H. So, at point E, H gets 0 value, but B is with finite value. So, at point E, H gets 0. So, at point E, so that is this one. At this time, the H is 0, but B is varying. Okay. And the point E stands for residual magnetism, that is minus BR. The point E stands for residual magnetism, that is minus BR. Okay. Next, of the magnetic core of material in opposite direction with respect to the previous case, and if the direction of which again reversed, okay, if the direction of H again reversed by reversing the current I, okay, if the direction of H again reversing, so here from this one we are again reversing, that is it is going to the positive direction, H by reversing the current I, then residual magnetism or flux density minus Br again decreases and gets 0 at point F following the path E to F. Okay, so it decreases again to 0. Okay, like that it is moving like this. So E to F, and next it is going to A. Okay, it is flowing like this. That is, it shows the path from E to F, that is this one. And next again further increment of H. So again I am increasing the increment value of H, that is the magnetizing force. The value of B increases from 0 to its maximum value. The value B increases from 0 to its maximum value of saturation level at a point A flowing path F to A. So that is this path F to A. So like this is in the second quadrant. Okay, F to A. And next, hard and soft material hysteresis slope are given below. So this one, okay, hard and soft. These are the types of hysteresis slopes we have. Okay, soft. So this BH curve gives a soft BH curve, and this curve gives the hard BH curve. So that is, so when current is increased from 0 value to a certain value. Okay, when current is increased from 0 value to certain value, then magnetizing force and flux density both are set up and increased following the path O to A. Okay, when current is increased from 0 value to a certain value, so magnetizing force and flux density both are set up and increased following the path O to A. Okay, so for certain value of current, flux density becomes maximum. Okay, for certain value of current, flux density becomes maximum. And the point indicates the magnetic saturation or maximum flux density of this core material. Okay, so all elements of the core material gets aligned perfectly at this condition. So when the value of current is decreased from its value of magnetic flux saturation, so H is decreased along with the decrement of B, not following the previous path, rather following the curve A to B. Okay, rather following the path A to B. So the point B indicates H is equal to 0 for I is equal to 0 with certain value of B. Okay, this lagging of B behind H is called hysteresis. Okay, the point B indicates H is equal to 0 for I is equal to 0 with a certain value of B. This lagging of B behind H is called hysteresis. So the point B explains that after removing of magnetic force, that is H, or magnetizing force H, the magnetism property with little value remains in the magnetic material, and it is known as residual magnetism, that is Br, or residual flux density Br. Okay, next, if the direction of current I is reversed, okay, if the direction of the current I is reversed, the direction of H also gets reversed. Okay, next, the increment of H in reverse direction following path B to C decreases, the value of residual magnetism that gets 0 at point C with certain negative value of H. So this negative value of H is called corrosive force, that is HC. Corrosive force, that is HC. So like that we are taking the hysteresis loops. Okay. So this is the concept of effect of nonlinear BH curve on magnetic material. Okay. Thank you. Thank you for watching this video. In the next class, I am going to discuss further topic, that is loss and losses in a transformer, and efficiency of a transformer, and maximum efficiency of a transformer, like that. Okay. Thank you.